Operational amplifiers, or op-amps. These are devices that are going to take an input signal, or really two sides of an input signal, and it's going to output an amplified or attenuated version of it. Amplification is where the voltage coming out is going to be greater than the voltage coming in, whereas attenuated is going to be the opposite. The output voltage from the op-amp is lower than that of the input. Now, there are other purposes for using op-amps, but for this course, this is generally what we are going to be using them for. Op-amps are going to be put into a circuit that the greater circuit's purpose is in part to amplify or attenuate our signal, and these circuits that we create with op-amps could be inverting or non-inverting. So it's possible, like in an inverting circuit, that the polarity of the input signal is going to be reversed. If it comes in positive, the output will be negative, and again, vice versa. Op-amps, or circuits with op-amps in them, can introduce lag into our signal. So our signal coming out is going to be delayed versus the signal that's coming in. Op-amps are typically powered devices. As the schematic of the op-amp shows, we typically have to supply it with some steady voltage in order for it to do its job, in order for it to amplify our signal. And here we see one amplification of an op-amp as an IC, as an integrated circuit. A common one here, the INA122. So it's going to have these 4 leads that is going to need power or our signal. And then if we see how it's used in the schematic, we're going to have a positive voltage in, a negative voltage in. Then we're going to have the source voltage or the powering voltage, which we are typically going to ignore in this class and assume that it's being powered, and then the output voltage. And what do we use these circuits with op-amps for? Well, the simplest case is simply amplifying or attenuating a signal, but more often we're going to be using these in active filters. So for example, a Butterworth filter is a classic example of a filter that is going to employ an op-amp. So the big picture of what we're doing here is we're going to have some signal coming into our circuit. Let's say that we are reading a sensor that's maybe a thermocouple or an accelerometer. We're putting it through our circuit that features an op-amp, and part of what we're trying to do is filter that signal. So there might be high frequency noise or low frequency noise in the original sensor's signal. We're passing it through our circuit in order to remove that high or low frequency noise. And then the other part of what we're trying to do is it's coming in at a very low voltage possibly, and it's going through our circuit, so it's going to be amplified, and then it's going to be high enough that we are able to read it into some device. So we'll get more into the use of these circuits when we get into the analysis section of the course in Unit 2, and specifically look at filters when we look at inputs that are sinusoidal or cosinusoidal. So that will be towards the end of Unit 2. So what we're worrying about now is how do we include them in our modeling? How do we get transfer functions when we have not only the LRC components that we were looking at, but now also these op-amps? In this course, we are going to deal only with the ideal op-amp. So in an ideal op-amp, these two assumptions are going to be, well, assumed to be true. It's going to let us model the effect that the op-amp has in our circuit and then on our transfer function. So typically we're going to look at op-amps with this sort of schematic. Again, we're going to ignore the power that is going to be required to operate them and just assume that that's being taken care of. So we're going to have our positive signal and our negative signal. Here I labeled it E1 and E2, and then our output E out. So we are assuming in an ideal op-amp that the input current is 0. We assume no current is going into the positive or the negative terminal of our op-amp when we are modeling them. And we are going to be assuming that the difference in the input voltages is 0. So that's to say that into the positive and the negative terminal, those voltages are the same. Now in reality, these two assumptions are not true, and in fact there has to be a difference between the positive and the negative here because the output voltage is going to be some K, which is part of what the op-amp properties are, times that difference between the negative and the positive. So in reality, that difference between E2 and E1 is not 0, but it is typically very, very small. But on the other hand, for an op-amp, it usually has a K value that's going to be very, very high. So for ideal op-amps, these assumptions are going to be used, and we're going to use them in order to decide what the voltages are, what the currents are around the op-amp. But be aware in actual op-amps that these assumptions are not actually true. The input current is not 0, and there is and has to be that small difference between the input voltage at the positive terminal and the input voltage at the negative terminal. Now, the modeling procedure when we have a circuit with an op-amp in it, I tend to do differently than how I did it for just a simple LRC circuit where maybe a loop using KVL and a current loop was pretty easy to employ to get the equations we needed. I think once there's an op-amp in the circuit, that becomes a lot more difficult to have these current loops happening. So I prefer to use nodal analysis when looking at circuits with op-amps. And I'll also be using nodal analysis when we get into fluid systems, because again, they're going to be set up in such a way that using these current loops is not really convenient. So the first thing that I like to do is label all the voltages at the nodes that I am able to identify. And this is where using that idea of an ideal op-amp is going to come in handy, because again, we're assuming that the voltages at the positive and the negative input terminals are equal. We'll also be able to mark anything connected to ground as having 0 voltage. And then we might come across nodes where we don't know the voltage as a number necessarily, and we can assign it some variable name that later we're going to be able to solve for. Then I can label the currents through wire when it splits, when it comes together. At the ideal op-amp, remember part of the ideal part was that there was no current going into the positive or the negative terminal, so the current through those parts of the wire has to be 0 to uphold that ideal op-amp. And then if we know where the current is in certain places, or we can say when it splits, we can give it new variable names that again we are going to be trying to solve as we're putting together our equations. And we want to simplify our circuit if we can using the equivalent impedances or using impedance blocks. And we're going to see often we can use a voltage divider to come up with some equations that are going to relate the voltages at different parts in our circuit. So like we saw before with just the resistor, when we have the voltage divider happening, we have an impedance block Z1 here and Z2. Here's connected to the ground, but it could be connected to any voltage. It wouldn't have to be 0, just using 0 here for some simplicity. But we can see that the voltage between V out and the ground is equal to that whole voltage from V in to the ground, or whatever the bottom voltage is here, times that ratio of the impedance now between V out and ground and the entire impedance in this part of our circuit. So as a recap, nodal analysis, going node to node, finding these voltage drops is going to be typically a better way to do the modeling and get our equations out when we have op-amps in our system.